Okay, so when we divide radicals, it also has some rules. It's going to be like the last one with multiplying, where you divide the coefficients, and then we use the quotient rule. So if you have the nth root of a divided by the nth root of b, and then the same roots, you can put those back together as the nth root of a over b. Likewise, if you have the nth root of a over b, you can split that back into the nth root of a over the nth root of b. And then you just simplify whatever remaining coefficient you may have left. So let's look at a couple of examples. Here's the first example. So, like it says, divide the coefficients. 12 divided by 2 is 6. And put them both underneath the same square root. And then you just reduce inside of the square root. So 160 divided by 5 is 32. And then you would reduce your radical. Half of 32 is 16. And then square root of 16 is 4. The 2 stays under. And this would give you 24 square roots of 2. And that's as far as you can simplify that one. You can have one, like example 2 over here, where they're both under, and check to see if you can just go ahead and divide. If you took 48 and divided it by 16, you would actually get 3. And you would check and see if you could simplify even more, like we did over here with the 32. If not, 3 is a prime number. That would be your answer. So if we look at this third example, 40 and 27 have absolutely nothing in common. They don't have any common factors. So let's do the opposite of the product rule and split them up. So this gives you the cube root of 40 over the cube root of 27. And then notice that 27 is actually a perfect cube. It's 3 cubed over, and then the cube root of 40, I'm going to do it over here. A perfect cube that goes into 40 would have to be 8 times 5. And the cube root of 8 is 2 cube roots of 5. So then this gives you 2 cube roots of 5 over 3. So let's look at these other 2 examples. Notice as well, 8 and 15 have nothing in common. So let's break that up into the square root of 8 over the square root of 15. From here, 15 isn't a perfect square and it doesn't have any perfect squares in it, but you don't want to keep any square root radicals in the denominator. So this is called rationalizing the denominator. If you only have one term, one radical, there's nothing being added or subtracted to the radical. It's just a monomial. Then you just multiply by the radical in the denominator on top and bottom. Using the product rule, 8 times 15 is 120. And then 15 times 15 would be 225. Okay, and so now we have the square root of 120 divided by the square root of 225. And from here, you would just simplify. So taking the square root of 120, you would find 2 perfect squares that goes into it. In this case, it's actually just going to be 4 and 30, which is going to give you 2 square roots of 30. This is going to become your new numerator. And then 225 is actually a perfect square. It is 15 squared. You cannot simplify this anymore. 2 and 15. 2 is not a factor of 15, and it doesn't go into 15, so this is it. So this would be your answer. And if you look over at example number 5, you can see that you have 3 over 2 square roots of 5. You have a square root in the denominator, and you can't simplify this anymore. So to remove it, you would just multiply by that exact same. Like you would just multiply by the radical in the denominator. You don't have to multiply by 2, just by the square root of 5. This is a coefficient. This is a radical. They cannot be multiplied together. It would actually just be 3 square roots of 5 over 2 square roots of 25. 5 and 5 are both underneath the radical, so you can use the product rule on those. And I noticed that the square root of 25 is actually a perfect square. It's 5 squared. So this becomes 3 square roots of 5 over 2 times 5, which then becomes 2 times 5 is 10. And then you would just check to see if you can reduce this anymore. And if you cannot, then this is your answer. This is it. So you just simplify until you can't simplify anymore. Okay, let's say, for example, that you have 3 square roots of 2 plus the square root of 6 over the square root of 12. Well, nothing can be simplified. You can't simplify anything here, but you still have a radical in the denominator. So to get rid of that radical, you do the same thing. Multiply by the square root of 12 on top and bottom. But notice how you have 2 terms in the numerator? So you're going to have to make sure you distribute to both of them. So this is a square root, and we have a square root here. So using the product rule, this gives us 3 square roots of 24. And product rule plus the square root of 72 all over the square root of 144. All right. And now it's just time to simplify, which I will simplify them down here. So we have a square root of 24. Perfect square that goes into 24 would have to be 4 and 6, which gives you 2 square roots of 6. And a perfect square that goes into 72, I would believe is 36. Half of 72 is 36, which becomes 6 square roots of 2. So we're going to go back up here, and we're going to replace the square root of 24 with 3 times 2 square roots of 6, and we're going to place the square root of 72 with 6 square roots of 2. And then if you notice the square root of 144 is a perfect square, it is 12. So multiplying right here, 3 times 2 is 6, square roots of 6, plus 6 square roots of 2 over 12. We have the same, and we have 2 radicals in the numerator, and they have the same index, but they don't have the same radicand, so they can't be added. But if you notice, you have a coefficient of 6, a coefficient of 6, and a coefficient of 12. And those 3 coefficients can be reduced by 6 to give you the square root of 6 plus the square root of 2 over 2. And there's nothing else you can do to simplify them. They have nothing in common, and then you no longer have a radical in the denominator. So this would be your answer. And then the last example. This time, instead of a monomial, just one term in the denominator, we have a binomial. We have 2 terms. To cancel out a binomial, you want to multiply by the conjugate, which the conjugate is the exact same term, except with this opposite sign. Voila. So when you multiply by the conjugate, the middle terms are going to cancel out, leaving you the first times the first and the last times the last. And then the numerator, make sure to distribute the 2. So this will leave you 12 plus 2 square roots of 5, that's a coefficient and a radical, over 6 times 6, minus square root of 5 times square root of 5. So following the product rule, 5 times 5 is the square root of 25 underneath the square root. And from here, you would just simplify the numerator if possible. And in this case, you actually can't simplify the numerator. 12 is a coefficient and 5 is a prime number. But in the denominator, notice how 25 is a perfect square. It's actually 5. And then you would just combine like terms. And 36 minus 5 is 31. And I did try to create problems that would resemble your homework a little bit to help you out. Let me know if you have any questions, but you can't reduce this any further. 31 is a prime number. And that would be your answer.